We live totally immersed in gases, don't we? From the air we breathe, the fizz in your soda, even the huge lift that carries a hot air balloon way up high.
Yeah.
These aren't just, abstract ideas.
Not at all. They're fundamental. Invisible forces really shaping our world constantly.
Absolutely. And today we're taking a deep dive into the fascinating science behind these gases. We're guided by insights from a leading chemistry textbook.
Right.
Our mission here is to kind of transform these complex principles into clear, concise understanding, basically giving you the shortcut to being truly well-informed.
And what's really remarkable, I think, is how just a few simple observations, things we see every day, actually led scientists to figure out these universal laws.
Yeah.
And those laws, in turn, inspired this really profound model to explain how gases behave right down at the molecular level.
Yeah.
It's like revealing this invisible dance of countless tiny particles.
It is amazing.
So we're going to unpack these fundamental principles today. We'll focus on the what and the why, and importantly, without needing diagrams or equations flashing on a screen, so you can really grasp the core ideas.
I find it incredible just how much is happening in the air right around us that we just can't see. So we'll start with the basics, like how we measure and describe gases.
Okay.
Then we'll journey through those foundational laws discovered by the early pioneers.
Boyle, Charles.
Exactly. From there, we'll build up to the elegant, ideal gas law, peer into that invisible world with the kinetic molecular theory.
The why.
Explore why ideal isn't always, real, and finally connect all of this to the atmosphere itself. The air that sustains us and the challenges it faces. Okay, let's dive in.
Let's do it.
So first off, what actually makes a gas? Well, a gas. We know it fills any container, it's easily compressed, mixes completely with other gases. But one of its most basic properties is that it exerts pressure.
Right, pressure.
Like, think about blowing up a balloon. The air molecules inside, they're constantly bouncing off the rubber walls, pushing outward, keeping it firm.
Mm-hmm.
Or, for a really dramatic picture, there's that classic experiment. You boil water in a metal can, fill it with steam, then seal it up tight and cool it down.
Oh, yeah, the can crusher.
Exactly. It collapses inward, like dramatically.
And that collapse is such a powerful way to see something we usually don't even notice.
Yeah.
The huge pressure of the atmosphere around us.
Right.
When the steam inside that condenses back into liquid water, there are hardly any gas molecules left inside pushing out.
So there's nothing pushing back.
Nothing pushing back. And suddenly, that external atmospheric pressure, this invisible force pushing on everything, just has no counterbalance, and boom, it crushes the can. It's a really vivid reminder of the sheer weight of the air column above us.
Wow. So if the atmosphere can actually do that, how on earth do we measure its pressure?
Well, that brings us to Evangelista Torricelli's brilliant invention, the barometer, back in 1643.
Oh.
Imagine taking a long glass tube, sealed at one end, filling it completely with liquid mercury, which is very dense, and then carefully inverting it into a dish also containing mercury.
Right. I've seen pictures of this.
Yeah. The column of mercury inside the tube doesn't empty out completely. It drops a bit, but then it stays up at a certain height.
Why does it stay up?
Because the weight of the entire atmosphere is pushing down on the surface of the mercury in the open dish. And that push balances the weight of the mercury column inside the tube.
Okay.
At sea level, on average, that column stays about 760 millimeters high.
So that height is the pressure measurement.
Exactly. That gave us our first common units of pressure, millimeters of mercury, or millimeters of mercury. We also call that unit the torr, to honor Torricelli.
Okay, mmHg torr.
Got it. And then we have the standard atmosphere, or atm, which is just defined as exactly 760 torr. And of course, for scientific work, the SI unit is the Pascal, or Pa. One atmosphere is about 101,325 pascals.
So that mercury column height literally showed us the weight of the air pushing down, which explains why a low-pressure system on the weather map means, less air pressing down, often bringing storms.
Right. The column would be lower.
And if you go up a mountain somewhere like Breckenridge, Colorado, that mercury column would be noticeably shorter, right? Because the air is thinner up there.
Exactly. Less atmosphere piled on top of you, so less pressure pushing down. It's a very direct, tangible link to something we usually just ignore.
Okay, so now we have a handle on pressure. Let's look at how gases behave when their conditions change. Scientists started noticing these really consistent patterns.
Yeah, empirical observations, things they could measure and repeat.
And from these observations came the foundational gas laws.
These laws are really the bedrock. They describe what gases do, based purely on experiment. They paved the way for understanding the why later on.
First up, Boyle's law. This comes from Robert Boyle, way back in the 17th century.
A long time ago.
He found that if you take a fixed amount of gas and keep its temperature constant, if you increase the pressure on it, the volume shrinks proportionally.
Think about a bicycle pump or just squeezing a balloon.
Right.
You push down, you decrease the volume, and you can feel the pressure inside go way up. It's an inverse relationship. Double the pressure, halve the volume, roughly.
Mathematically, it's PV equal K, where K is some constant value for that specific gas sample at that temperature.
Exactly. Now, it's worth mentioning, while Boyle's law works incredibly well for many practical purposes, real gases only follow it perfectly at very low pressures.
Ah, okay. So it's an idealization.
It is. At higher pressures, things get a bit more complicated. Those little deviations were actually crucial clues that the simple ideal picture wasn't the whole story. We'll circle back to that.
Okay. Next up, we have Charles's law, named after the French physicist Jacques Charles.
Around the late 1700s.
He discovered that if you keep the pressure and the amount of gas constant, the volume of a gas increases linearly with its temperature.
This is the hot air balloon principle, right?
Exactly. Heat the air inside the balloon, its volume expands, it becomes less dense than the surrounding cooler air, and that buoyant force makes the balloon rise.
And Charles's experiments led to something absolutely fundamental. When he plotted gas volume versus temperature in Celsius for any gas he tried,
Yeah.
he found that if you extrapolated the straight line graph backwards, they all hit zero volume at the exact same theoretical temperature, minus 273.15 degrees Celsius.
Wow, the same point for all gases.
The same point. This unique temperature was defined as absolute zero. The bottom of the temperature scale, 0 Kelvin. It's the theoretical point where all molecular motion would cease.
And that's why we use Kelvin for gas laws.
Absolutely critical. You must convert Celsius to Kelvin. K equals C plus 273.15, or often just 273 is close enough for any gas law calculation involving temperature. Charles's law is V's BT, where T is in Kelvin.
Got it. Kelvin is key. Okay, our third foundational law is Avogadro's law.
Named after Emilio Avogadro. This relates volume to the amount of gas.
Right. It states that for a gas at constant temperature and pressure, its volume is directly proportional to the number of moles of gas particles.
It's beautifully simple. V Weeman N, where N is the number of moles. Double the moles, double the volume, assuming T and P don't change.
So this means if you have two identical balloons, same temperature, same pressure, and one's filled with 1 liter of lightweight helium and the other with 1 liter of much heavier nitrogen, they actually contain the exact same number of gas particles, the same number of moles.
Precisely. Doesn't matter what the gas is, just how many particles there are. Equal volumes contain equal numbers of molecules under the same conditions. This insight was revolutionary for understanding chemical reactions involving gases' stoichiometry.
Okay, so we've got Boyle's law relating pressure and volume.
TV.
Charles's law relating volume and temperature.
VB in EWT.
In Kelvin.
Yeah.
And Avogadro's law relating volume and the amount of gas, the moles. Now, here's where it gets really neat. You can actually combine all three of these empirical laws into a single, incredibly powerful equation.
The ideal gas law. This is a real cornerstone of chemistry.
It looks like PV equals nRT.
That's the one. It connects all 4 key variables: pressure P, volume V, number of moles N, and absolute temperature T.
And what's the R?
R is the universal gas constant. It's the proportionality constant that makes the units work out and links everything together. Its value depends on the units you use for pressure and volume, but a very common one is 0.08206 lm/kmol.
Liter atmospheres per Kelvin mole. Okay.
This single equation, TVNRT, is incredibly versatile. It's an equation of state. It describes the condition or state of a given amount of gas.
So if you know any three of those variables, PV and nRT, you can just calculate the fourth one.
Exactly. Or you can use it to predict how a gas will change if you alter one condition while holding others constant. It's also fundamental for gas stoichiometry, figuring out volumes of gases produced or used up in chemical reactions.
That seems super useful, like calculating how much CO2 gas you'd get from decomposing a certain amount of limestone.
Precisely. And there's a handy shortcut often used: standard temperature and pressure, or STP.
Right, I remember that. What is it again?
STP is defined as exactly 0 degrees Celsius, which is 273.15 K, and 1 atmosphere of pressure.
Okay.
And at STP, it turns out that 1 mole of any ideal gas occupies a volume of 22.42 liters.
22.4 liters per mole at STP. That's a good number to remember.
It is. It simplifies lots of calculations if you know the reaction happens under those specific conditions.
And you mentioned something else cool. You can figure out the molar mass of an unknown gas using this.
Absolutely. Remember, density is mass divided by volume, d/n or dV, and the number of moles, N, is mass, M, divided by molar mass, MM.
Okay, yeah.
If you rearrange the ideal gas law, PV in RT, and substitute those relationships, you can derive an equation that relates density, temperature, pressure, and molar mass. So if you measure the density of an unknown gas at a known T and P,
You can calculate its molar mass. That's like giving it a fingerprint.
it really is very powerful for identifying substances, especially back when more sophisticated techniques weren't available.
Okay, so PV&RT handles single ideal gases beautifully. But what happens when you have a mixture of gases, like the air we're breathing right now, or that special mix a scuba diver uses?
Good question. That brings us to Dalton's law of partial pressures.
John Dalton.
The very same. His law is actually quite intuitive. It states that the total pressure exerted by a mixture of gases is simply the sum of the pressures that each individual gas would exert if it were present alone in the same container.
So P total equals P1 plus P2 plus P3, and so on for all the gases in the mix.
Exactly. P total, I pi. Each gas contributes its own partial pressure to the total.
Why does that work?
It goes back to the ideal gas assumptions. If the gas particles have negligible volume and don't interact with each other, then each gas molecule flies around and hits the walls independently of what other types of molecules are also in there. Their pressures just add up.
Okay, that makes sense. And this is really important for things like scuba diving, right?
Critical. Deep-sea divers breathe mixtures, often of helium and oxygen, heliox, instead of regular air, nitrogen and oxygen. This is to avoid nitrogen narcosis and decompression sickness, the bends.
Right.
Dalton's law allows them to calculate and control the partial pressure of oxygen very precisely, ensuring they get enough to breathe, but not so much that it becomes toxic at the high pressures experienced deep underwater. Same goes for managing the inert gas, helium.
So how do you know how much pressure each gas contributes?
That's where the concept of mole fraction comes in. It's symbolized by the Greek letter chi.
Chi. Okay.
The mole fraction of a particular gas, say gas 1 in a mixture, is just the number of moles of that gas, N1, divided by the total number of moles of all gases in the mixture, N total. So one other and one untotal.
And how does that relate to pressure?
Well, it turns out the partial pressure of a gas, P1, is simply its mole fraction multiplied by the total pressure, total, P1 less 1 per total.
Okay. So if air is about 78% nitrogen molecules,
By mole fraction, yes, roughly N2 is 0.78.
then the partial pressure of nitrogen is just 0.78 times the total atmospheric pressure.
Exactly right. Around 0.78 at any area at sea level.
That's useful. What about in the lab? I remember doing experiments where we collected gas over water.
Ah, yes. A very common technique for collecting gases that don't dissolve well in water, like hydrogen or oxygen produced in a reaction.
But you don't get just the pure gas, right?
Correct. When you collect a gas over water, the bubbles rise and fill the collection container. But that space also contains water molecules that have evaporated into the gas phase. You get a mixture of your desired gas and water vapor.
So the pressure inside is the gas pressure plus the water vapor pressure.
Precisely. The total pressure inside the container, which you usually adjust to equal the atmospheric pressure outside, is the sum of the partial pressure of your collected gas and the vapor pressure of water.
And water's vapor pressure changes.
It depends strongly on the temperature. You have to look up the vapor pressure of water at the specific temperature of your experiment and subtract it from the total measured pressure to find the true partial pressure of the gas you actually collected.
Okay, gotta remember that correction.
It's important for getting accurate results. And again, the fact that Dalton's law works so well for mixtures reinforces those ideal gas assumptions. Particle volume doesn't matter much, and intermolecular forces are negligible, at least under many conditions. These were all vital clues for developing the next big idea.
The theory behind it all. We've talked a lot about what gases do the laws they follow, but the deep dive is about understanding why.
Exactly.
And that's where the kinetic molecular theory, or KMT, comes in. This is the model scientists developed to explain why gases behave the way the laws describe.
Right. KMT paints a picture of what's happening at the microscopic level with the individual gas particles. It makes a few key simplifying assumptions about an ideal gas.
What are those assumptions?
Okay, first, gas particles, atoms or molecules, are assumed to be so tiny compared to the distances between them that their actual volume is considered negligible, essentially zero. Think of them as points in space.
Okay, tiny particles, lots of empty space.
Second, These particles are in continuous, rapid, random, straight-line motion. They are constantly moving and colliding with each other, and importantly, with the walls of their container.
And those collisions with the walls, that's pressure.
That's exactly where pressure comes from. The combined force of billions upon billions of these tiny collisions per second on the container walls.
Makes sense.
Third, the particles are assumed to exert no forces on one another, either attractive or repulsive, except during the instant of collision. Between collisions, they just fly past each other unaware. Collisions themselves are perfectly elastic, meaning kinetic energy is conserved.
No stickiness, no pushing away, just perfect bounces.
Ideally, yes. And fourth, and this is crucial, the average kinetic energy of the gas particles is directly proportional to the absolute temperature in Kelvin.
Ah, so temperature is motion.
Temperature is a measure of the average kinetic energy of the particles. Hotter gas means, on average, the particles are moving faster. Colder gas, they're moving slower, on average.
Okay, so how does this particle picture explain the gas laws we talked about?
Beautifully, actually. Let's take Boyle's law, PVK at constant T and N.
Pressure and volume.
Right. If you decrease the volume, squeeze the container, the particles have less distance to travel before hitting a wall, and they're crammed into a smaller space, so they hit the walls more frequently. More collisions per unit area per second means higher pressure. Matches the law perfectly.
Okay, how about Charles's law? VBT at constant P and N.
Volume and temperature. If you increase the temperature, the particles gain kinetic energy, so they move faster and hit the walls harder and more often.
Right.
To keep the pressure constant, meaning the same force per unit area from collisions, the volume must increase, giving the faster-moving particles more room to spread out the collisions. Again, matches the law.
Cool. And Avogadro's law, Vn at constant T and P?
Volume in moles. If you add more gas particles,
Uh-huh.
increase N at the same temperature and pressure, you need more space to accommodate them if you want to keep the collision rate against the walls, the pressure, the same. So the volume must increase proportionally.
Yep.
And Dalton's law of partial pressures. Since the KMP assumes particles have no volume and don't interact, it simply doesn't matter what type of particles they are. Nitrogen hitting the wall or oxygen hitting the wall, they're at the same temperature, they contribute to pressure based just on how many there are and how fast they're moving. Their individual pressures just add up.
Wow, okay. So KMT provides a really satisfying why for all those empirical laws.
It really does. And it gives us that profound connection between the macroscopic property we measure temperature and the microscopic reality of molecular motion. Kelvin temperature is average kinetic energy.
That's amazing. And does KMT tell us how fast these particles are actually moving?
It does. We can calculate the root mean square velocity, often written as arms. It's a type of average speed for the particles. The formula involves the temperature, the molar mass of the gas, and the gas constant R.
So does that mean lighter gases move faster?
Exactly. At the same temperature, all gases have the same average kinetic energy. But kinetic energy depends on both mass and velocity. Ke equals 12 millivs out. So for lighter particles, smaller m, to have the same average Ke as heavier ones, they must have a higher average velocity, larger v.
Like hydrogen molecules versus oxygen molecules at room temperature.
Hydrogen molecules will be zipping around much, much faster on average than the heavier oxygen molecules.
And we can see evidence of this.
Oh, definitely. Two phenomena clearly show it: effusion and diffusion. Effusion is the process where gas escapes from a container through a tiny pinhole into a vacuum.
Okay.
Graham's law of effusion states that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. Basically, lighter gases escape faster.
Because they're moving faster and hit the hole more often?
Pretty much. And diffusion is the gradual mixing of gases due to their random motion. If you open a bottle of ammonia at one end of a room and, say, perfume at the other, you'll eventually smell both everywhere. But the lighter ammonia molecules generally spread out faster than heavier perfume molecules.
I remember a demo like that, with ammonia and hydrogen chloride gas in a long tube.
Ah, the classic ammonium chloride ring experiment. You put cotton soaked in ammonia, NH3, molar mass, about 17 gmol at one end, and cotton soaked in hydrochloric acid, which produces HCl gas, molar mass, about 36.5 gmol at the other.
And a white ring forms where they meet.
Right, the white solid ammonium chloride, NH4CO. But the ring doesn't form exactly in the middle. It forms closer to the HCl end.
Because the later ammonia traveled further down the tube in the same amount of time.
Precisely. A beautiful demonstration of Graham's law and the fact that lighter molecules move faster.
Okay, KMT and the ideal gas law seem like a really powerful combination. But you mentioned earlier that real gases aren't always ideal.
That's right. The KMT model is just that, a model. A very useful one, but it makes simplifying assumptions that aren't perfectly true for real gases, especially under certain conditions.
When does the ideal model start to break down?
Mostly at high pressures and low temperatures.
Why then?
Well, think about the KMT assumptions. At high pressure, the gas molecules are forced much closer together. That assumption that the particle volume is negligible compared to the space between them starts to fail. The particles themselves actually take up a significant fraction of the container volume.
Okay, so their own size becomes important.
Exactly. And at low temperatures, the particles are moving much more slowly. When they pass close to each other, those weak intermolecular attractive forces, which KMT ignores, have more time to act. They start to stick together slightly, or at least influence each other's paths.
The no interaction assumption fails too.
Correct. So if we actually measure the PVN in T for a real gas and calculate the ratio PVNRT, ideally it should always equal 1.
But for real gases?
For real gases, that ratio deviates from 1, especially at high P and low T. Plotting PVNRT versus pressure shows these deviations clearly.
So scientists needed a better equation for real gases.
Indeed. And Johannes van der Waals came up with a brilliant modification of the ideal gas law in 1873. His equation introduces correction factors to account for those two failed KMT assumptions.
How does it work?
The van der Waals equation adjusts both the pressure and volume terms. For the volume, it subtracts a term NB from the container volume V. Here, N is the moles of gas, and B is the van der Waals constant representing the actual volume occupied by a mole of those specific gas molecules. It's like correcting for the excluded volume.
Okay, so it accounts for particle size. What about the attractions?
For the pressure, it adds a correction term, AV, to the measured pressure observed. The constant A reflects the strength of the intermolecular attractive forces for that particular gas. This term essentially accounts for the fact that attractions reduce the force of impact with the walls, making the observed pressure lower than the ideal pressure would be.
So the equation looks more complicated, but it matches reality better.
Much better, especially under non-ideal conditions. The full equation is PA observed plus ANV VNB equals nRT. And the values of A and B are different for each gas. They tell you something fundamental about the molecules themselves. A large A means strong attractions. A large B means large molecules.
That's really clever. It shows how science works. Build a model, test it, see where it fails, and then refine it.
Absolutely. It's a beautiful example of that iterative process, deepening our understanding by acknowledging and correcting for the simplifications we made initially.
Okay, let's bring all this fantastic gas chemistry back to Earth, literally, to the most important gas mixture we know, our atmosphere.
Right. Primarily nitrogen, about 78%, and oxygen, about 21%. But those trace gases like argon, water vapor, carbon dioxide, methane, they play incredibly important roles too.
Our atmosphere isn't uniform either. It's layered.
It is. Temperature changes quite dramatically with altitude.
Yeah.
We live down here in the troposphere where weather happens. Above that is the stratosphere, which contains the vital ozone layer.
Ozone, O3, that protects us from UV radiation, right?
Exactly. It absorbs most of the harmful high-energy ultraviolet light from the sun. Without it, life on the surface would be very difficult, if not impossible. But down here, in the troposphere, the chemistry gets strongly influenced by, well, by us.
Human activities. This is where air pollution comes in.
Unfortunately, yes.
Mm-hmm.
Our industrial civilization, our transportation, our power generation, they release enormous quantities of various gases and particulate matter into the atmosphere.
What are the main culprits?
Two huge ones are transportation, the combustion of gasoline and diesel in cars and trucks, and electricity production, especially burning coal.
What do they release that's so bad?
Well, vehicle exhaust contains nitrogen oxides, mainly NO and NO2, collectively called NOx. It also releases unburned hydrocarbons and carbon monoxide.
And these lead to smog.
Yes, specifically photochemical smog, that hazy brown stuff coming in sunny cities with lots of traffic. It's a complex process driven by sunlight.
How does sunlight play a role?
Sunlight can break down nitrogen dioxide, NO2. This produces nitric oxide, NO, and highly reactive single oxygen atoms.
Just O, not O2.
Just O, extremely reactive. These O atoms then slam into regular oxygen molecules, O2, to form ozone, O3.
But wait, I thought ozone was good in the ozone layer.
Good up high, bad nearby. Ground-level ozone is a major component of smog and is harmful to breathe. It irritates lungs, aggravates asthma, and damages vegetation.
So ground-level ozone is a pollutant created indirectly.
Correct. And it doesn't stop there. Ozone itself is reactive and can contribute to forming other nasty things like hydroxyl radicals,
So,
which then react with those unburned hydrocarbons from exhaust, creating a complex soup of irritating chemicals.
yikes. Okay, what about the coal-burning power plants?
A major issue there is sulfur. Coal naturally contains sulfur compounds. When it burns, it releases sulfur dioxide, SO2 gas.
SO2, what does
Yeah.
that do?
In the atmosphere, SO2 can be oxidized, often with the help of catalysts like dust particles, to form sulfur trioxide, SO3.
Okay.
And SO3 reacts very readily with water vapor in the air to form sulfuric acid, H2SO4.
Sulfuric acid falling from the sky.
Essentially, yes. This is the main component of acid rain. Nitric acid formed from NOx emissions also contributes.
And acid rain is terrible for the environment.
Devastating. It can make lakes and streams too acidic for fish and other aquatic life to survive. It damages forests, harms crops, and even corrodes buildings, statues, bridges, anything made of limestone, marble, or metal.
Wow. It sounds pretty bleak.
It can be, but it's not all doom and gloom. The crucial point is that understanding this atmospheric gas chemistry allows us to find solutions.
Like what?
We'll think about the U.S. Environmental Protection Agency, EPA, and the Clean Air Act. Regulations based on scientific understanding have led to significant improvements. Technologies like catalytic converters in cars drastically reduce NOx and hydrocarbon emissions. Power plants have installed scrubbers to remove SO2 from their exhaust before it reaches the atmosphere.
And has it worked?
Yes, remarkably well in many cases. Since the Clean Air Act amendments of 1990, for example, emissions of key pollutants like NOx and SO2 in the U.S. have actually been cut by roughly 50%, even while the economy and population grew.
That's actually really encouraging.
It absolutely is. It shows that when we understand the chemistry, we can develop effective strategies to mitigate the problems. It's a powerful testament to the practical value of this science.
What an incredible journey we've taken, seriously, through the whole world of gases, from just breathing or inflating a tire,
Simple X.
all the way through Boyle's law, Charles's law, Avogadro's law, combining them into the powerful ideal gas law. Then peering into the why with the kinetic molecular theory, seeing how particles move.
Temperature as kinetic energy.
Understanding why real gases sometimes deviate and how van der Waals fixed the model.
Accounting for size and attraction.
And finally, connecting it all to the vital, complex, and sometimes vulnerable chemistry of our own atmosphere.
It really shows that whole scientific process, doesn't it?
Mhm.
You start with observations, you formulate laws, you build a model to explain them, you test the model, find its limits, and then you refine it.
Yeah, constantly learning and improving the picture.
Exactly. And seeing how crucial it is to look at these things from different angles, the macroscopic laws, the microscopic theory, the real-world implications.
So for everyone listening, what's the big takeaway? Next time you feel the wind or you see steam coming off hot water, or honestly, just take your next breath.
Yeah.
Just maybe pause and remember that incredible invisible dance happening all around you. Billions of gas molecules, their pressure, their volume, their temperature, their interactions, constantly shaping everything.
It's quite profound when you stop to think about it. And it does raise an interesting question for the future, doesn't it?
Oh, what's that?
Well, if our understanding of gas chemistry has already allowed us to significantly reduce harmful air pollution, what might the next level of understanding and technological advancement bring?
Cool.
Could we move beyond just mitigation? Could advancements in things like atmospheric modeling, gas capture, maybe even conversion technologies allow us to perhaps more actively manage or even fine-tune atmospheric composition on a larger scale someday? Maybe for optimizing health or stabilizing climate in new ways?
Wow, moving from fixing problems to actively optimizing the atmosphere. That is definitely a thought-provoking idea to leave people with.
And something to ponder.
Absolutely. We really hope this deep dive has given you a new appreciation for this unseen world of gases. Thank you so much for joining us on the deep dive.
Thanks, everyone.
And a big thank you from the entire Last Minute Lecture team.